in 6.3, we were talking about similar triangles and other figures. Now, we spend a lot of time talking about congruent figures. Today, we're looking at similar figures. So we should be able to, by the end of this lesson, be able to identify and solve similar figures. So going back to congruent, those are the first type that we talked about. So congruent figures are the same size, same angles, same lengths of sides. Everything is the same except the orientation. So if we do a rotation, so if we take a figure and we spin it, we rotate it, it's still congruent, still the same size. If we reflect it or flip it over, it's still the same size. And same with translation. So if we shift it right or left or up or down, it's still going to be congruent. So when we're looking at similar figures, it's the same idea. However, we have similar figures when we do all of those translations as well, or transformations, as well as we're going to include dilations, since that's what we focused on last time. Similar figures, we can also use dilation, so they can be different sizes. So we are going to be looking at some ideas here. So we have, just like we talked about, we add the dilations into that factor. So we have a couple conjectures, which I want you to pause the video after we've talked about them and see if you can think about which ones you think are true. So conjecture number one is saying that all rectangles are similar. Remember, we can rotate it, reflect it, translate it, and dilate it. So remember, dilations, we're multiplying everything by the same number. All the sides get multiplied by the same number. Conjecture 2, all equilateral triangles are similar. Isosceles triangles are similar, and all squares are similar. So go ahead and pause, think about which ones you think are true. And I want you to actually mark them so that later when we come back to them, we're going to talk about each of them and figure out which ones are true, which ones are not. So Mason, he is going to be first talking about number 1, which is the rectangles. All rectangles are similar. So his idea is that if we take this rectangle on the left and we place it on top of this rectangle on the right, line up the corners. So we're going to line up corner A with corner Q. We're going to line those up. And then he said if we place this on top and then if we take that corner, we can stretch it all the way out until we get to S. And then that means that they'd be similar. So what do you think? Does that mean they're going to be similar? If I use dilation, is that going to work? If I dilate that all the way out to the corner? The answer is no, actually not, because in a dilation, this side right here has to be dilated by the same scale factor as this side. So if I try and stretch this out onto the bigger rectangle, I have to stretch farther this way than I do this way, and that's just not going to work out. So since we can't multiply everything by the same scale factor, then this is an example of why it is not going to work for rectangles. So this is a no for rectangles because the dilation has to be consistent. A constant scale factor for all sides. Okay, so now the next thing we have to talk about is equilateral triangles. So Mia is talking about equilateral triangles, and she has an explanation as to why she thinks this is true. Okay, so we know that all equilateral triangles have 3 60-degree angles. So she's going to take triangle ABC, and she's going to rotate it a little bit, and we're going to land this corner on top of this corner. So we're going to kind of fit it in the corner over here. So ABC. And then she says she is going to dilate it, stretch out, A as the center of dilation, and she's going to stretch this out this way, this out this way. So it ends up landing on top of the bigger triangle. So we know they have the same angles, so that's good. So they do fit on top of each other. We just need to know, is the dilation going to work for equilateral triangles? And the answer is yes for all equilateral triangles. it works because we know these angles are also going to land on top of each other. They're also going to fit within each other because they are all the same, all 60 degrees. So that's good. And we know that all of the sides are the same. That is important as well. Oh, these are the same as each other because when we dilate it, they're all going to be dilated the same amount. We're going to be dilating by the same scale factor. So after I scale it, they will end up still being the same length. Okay, so number 4, let's talk about isosceles triangles. And isosceles triangles can look similar, but they can also be very different. So isosceles just means we need 2 sides that are the same. So let's say we have these 2 sides that are the same of this triangle right here. But we can also have like a super tall skinny triangle where these 2 sides are the same. So obviously I can't stretch these 2 out to look like each other. So with a similar triangle, remember they can be bigger or smaller, but it has to be the same shape. And those are definitely not the same shape. The scale factor would not be consistent. But squares, just like we talked about with the isosceles triangle, it's important that they have all the same angles. But also squares are similar because they have equal sides, so that when you scale, when you multiply by a scale factor, they will all be scaled exactly the same and they will end up exactly the same. So isosceles triangle is a no, squares are a yes. Okay, so on to the next page. So we talked about 2 different things. We talked about angles and we talked about sides. So this is important. We are looking at, when you look at 2 polygons that are similar, trying to decide if they're similar, we can say that they are similar if all corresponding angles are congruent. So the angles is the first thing that we need to look at. And the next thing that we need to look at are our sides. So all corresponding pairs of sides are not congruent, but they are proportional. So there's a very big difference between those 2, but it's important we know the difference. So angles are going to be congruent, sides are going to be proportional, all of them. So if we are going to be looking at proportional sides, we need to remember how to solve proportions. So in this example, a proportion is just a fraction equal to another fraction. We can solve these by cross multiplying. And how that works is we multiply across, so 3 times 7, which is 21, and we still have our equal sign in the middle, and then we multiply across this way, equals 8 times x. And now we have a new equation we just solve, so we divide by 8 on both sides. That cancels, and we get x equals, this doesn't reduce, so we can just leave it as 21 over 8. Let's try this next one. It's still a fraction equal to a fraction, even though it's a little bit more complicated of a fraction, but so we can still cross multiply. So let's do 4x times 3, which is 12x, and then equals, keep the equal sign in the middle, and then 9 times this over here. So we can either distribute that 2x before we do the cross multiplication, or let's actually do that. I'm going to rewrite this. I'm going to distribute this and say this is actually 2x plus 8. So now when I do the 9 times the 2x plus 8, the big thing that happens here, and this is the mistake that you're going to make. If you're going to make a mistake, it's going to be here. So the 9 has to be multiplied by the whole thing, by both terms up there. So it has to be distributed. So the 9 times 2x gives me 18x, and then the 9 times 8 gives me 72. And then we solve. So we get our x's together by moving them onto the same side. So I get negative 6x equals 72. Divide by negative 6. X equals negative 12. So here's the next one. Go ahead and pause and try this one on your own, and then we'll go through it. Again, when you have 2 terms, you have to make sure the 7 gets multiplied by both of them. So 7 times x, also 7 times 4, which is 28. The equal sign still stays in the middle, and then we multiply this way. Again, make sure the 9 gets multiplied by both of those. So 9x minus 9, and then you solve. So I'm going to move my 7x so I can get my x's together. And then I can get the x by itself by moving the 9. So that would give me 37 equals 2x. Divide by 2 to get the x by itself. This doesn't simplify either. You can give me a decimal or you can leave it as a reduced fraction, which is 37 over 2. So that is how we solve proportions. We are going to be writing those and solving those as we look at our similar figures. So we have similar figures, and again, it's a review. Similar figures have the same angles, but they do have different sides. So again, the angles have to be the same, but the sides are going to be different, but they are proportional. Here's the symbol right here for similar. It's just the squiggle. So it's like the squiggle that's on top of the congruent sign. So similar triangles are triangles that have 3 pairs of congruent. Which part of it has to be congruent? Those are the angles. Has to be 3 pairs of congruent corresponding angles and 3 pairs of proportional corresponding sides. Our sides are proportional. Corresponding, when we say corresponding, it means they are in the same place or the same location. When you're looking from one triangle to another or from one figure to another, we'll say same location. So like here we have angle A, and then when the triangle is shrunk on the right side, that is corresponding with angle D. And you notice the measures are the same, even though one triangle is bigger and one is smaller. Okay, and then proportional means the sides will have the same scale factor or the same proportion. So as we're looking at these triangles down here, we have the big one on the left, the small one on the right, and we have all the proportions of our sides. So side AB divided by DE is congruent to side BC divided by EF. Those are corresponding. And then CA and FD are also corresponding. And then we also have listed all of our angles that are corresponding. So A corresponds to D, so we talked about that before. B corresponds with E, because those are the same size, and then C corresponds with F, because those are the same size. So it's so important that we remember this as we write out our triangle. Triangle ABC is congruent to, or sorry, not congruent, but is similar to, but you have to, we have to use these letters, D, E, F, but we have to make sure we're using them in the right order. So if A comes first, then what A is corresponding to has to come first in our second triangle. B is second, so we have to use E second. And then C is third, so then comes triangle D, E, F. So we have to make sure that those all line up with each other. Okay. So let's look at our examples on the right. So find all the missing sides and angles, and they tell us that these two triangles are similar, so we know that ahead of time. So again, if J is first, that's going to correspond with M. So let's look at J and M, make sure they are corresponding. Check they are, because they are the same size. Okay, let's look at K and N. Those are going to be corresponding, so we have K here and here. Okay, so it looks like we're missing angle N, but since K is 60, we also know that N is going to be 60. And then L corresponds with O. So we don't have either one of those. However, we do have two angles of our triangle. So if we just take 180, subtract the two angles that we do have, that will give us whatever we have left, which I believe is 45. Whatever we have left, that's going to be what we have left over for angle L, which is going to be the same for angle O. Okay, now we need to find our missing sides. So sides are different. They are not congruent, but they are proportional. So as we look at sides, we do have one proportional one pair of sides. So because I know that JL corresponds with MO, so in setting up my proportions, I can say 9/3 equals And then this is a little bit more of a simple one because you can tell like what was it that I multiplied to get from 3 to 9 or so on. You can go backwards. What did you divide 9 by to get to 3? And we multiplied by 3. So if we just keep that in mind, if I know this side is 1, so I'm going to keep my proportions up over here. So I'm going to put that on the bottom because that's from the same triangle as 3. Then what is that going to correspond to over here? And that's going to be 3. 9 over 3 is 3, so 3 divided by 1 is going to be okay. And that has to be congruent to our last set of sides. So we have this one, which comes from this triangle. So 6 divided by 2 makes all of these fractions equal to each other. So there's all our missing sides and angles. And then down here, this is just practice identifying when we are given similar triangles, how we match it up. So if I'm looking at angle Q, that's going to be congruent to angle X, so on and so forth. So I'm looking at Y, that's congruent to angle R. Here it's using all 3 letters to write out an angle. So we use all 3 corresponding. So R corresponds with Y, S corresponds with Z, and Q corresponds with X. And so I use those same letters when I'm filling out my proportions over here. QR corresponds with XY. RS is YZ. SQ is ZX. All right. Let's see if we can identify some similar triangles now. Okay, so just like when we were talking about congruent triangles and identifying from like side angle side or side 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 or angle side angle, we didn't have to have every piece of information on the triangle to find out that they were congruent. So it's the same thing here. We do not have to know all 6 pieces of a triangle to prove they are similar. And there are 3 ways to prove triangles are similar, and they are shown below. So we have side, 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 angle, side, and then we have angle, angle, which is also known as angle, angle, angle. Okay, these look similar to the other ones. However, when we're looking at side, 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 remember with similar triangles, they do not have to be congruent, but all 3 pairs have to be proportional. Okay, here we're going to have 2 pairs of sides, but then we're going to have the angle between them. So looking at the sides have to be proportional. But the angles, remember, have to be congruent. The angle between them has to be congruent. And when we're just looking at angles, we can either have 2 pairs of angles that are congruent. But we know if we have 2 angles, we can also like automatically find out that 3rd side. So pretty much AA or AAA, those are representing the same situation. So we can also say it if all 3 are congruent. It would be the same statement. So let's look at these pairs of triangles over here and see if we can determine whether or not they are similar. So we have 1 pair of angles that are congruent, and we also have, even though it doesn't have it marked, we know these are vertical angles, so we can say those are congruent. So it looks like we have 2 pairs of angles that are congruent. And that is on our list over here of things we can use. If I have 2 pairs of angles that are congruent, I can say these 2 triangles are similar. So this is a yes. They are similar. On number 2, I have no angles, so we're hoping that these sides are going to work out for a side, side, side kind of deal. Okay, so what I need to do to check the proportions here is I'm going to take all 3 sides of this first triangle over here, 14, 12, 7, and I'm going to divide them by the corresponding sides on the other triangle. So 10.5, that's the longest one, and then 12 corresponds with 9, 7 corresponds with 5.25. So if you type that in your calculator, 14 divided by 10.5, 12 divided by 9, so on and so forth, you end up getting the very same decimal. And it doesn't matter if it's a crazy decimal, just as long as it's the same number for all 3. So in this case it is, so check, these triangles are similar by side, side, side. On this one, we are only given 1 angle and 1 pair of sides. And there's nothing else that I can figure out. I can't figure out if any of the angles are congruent, and without being given the sides, I can't figure out anything for those either. So this is just not enough information. They could be similar, but we just don't know enough. So this is going to be a no. Can't decide. We don't know. All right. So a couple to practice. So we have some triangles here that are similar. They tell us at the beginning they are similar. And we have to find x, y, and z in this case. So we have x and y, which are both angles, and then we have z over here, which is a side. So let's look at sides first. So I have a side here and a side here. So I'm assuming that's what I'm going to use in my proportion. So 5 and z are coming from the same triangle, so I put those both on top. And then I have to figure out what corresponds with them. So 5 came from side AB. If I'm looking up here, AB corresponds with DE. So that's going to correspond with this one. So I'm going to put the 7 on the bottom of this one. And hopefully, well, we're going to make these, well, we know they are similar. So that is going to be equal to whatever Z is corresponding to. So Z is our AC. So if we look at AC, that's going to correspond with DF. So that's this guy over here. So we're going to put a 15 on the bottom of that one. And we just set up a proportion to solve for our missing side. So now we cross multiply. So 5 times 15, which is 75. Keep the equal sign in the middle. And then we have 7 times z. And all we have to do now to solve for z is divide by 7. And that doesn't work out nicely either. So I'm just going to leave it as 75 divided by 7. There's my z. All right, now I need to go back and find my angle. So I'm looking for x. Let's do that one. So x is angle D. So looking at angle D up here, that should be corresponding to angle A. So looking at angle A over here is 95, so we can just say x is 95. And same idea for F. Angle F, if we look at F right here, that corresponds with C because they are both third. So C over here is 33 degrees. So we can just say y equals 33. And then we're good to go. So check this statement up here to figure out what corresponds. Over here, same idea. Go ahead and pause and see if you can do this on your own. But we need to solve for x and y. So I'm going to do x first. That's our side. So I'm going to take x and 13. They are from the same triangle, so I'm going to put those on top. X is our MN side, which corresponds with JK. So I'll put that on the bottom of the x. And that is going to equal 13 goes from O to N. So these two right here, O to N. So that's going to match K to L, K to L. So that's going to match 10. Okay, and we multiply, go from there. So 10 times x equals, I think this is 110.5. And then we solve for x, divide by 10, divide by 10. So we get x equals 11.05. And then we still have our y to solve for. So y is an angle, and that is angle M. Angle M corresponds with angle J. And you can see, you don't have to look at the similarity statement at the top. Sometimes you can see, just according to the shape of the triangles, which angles correspond with each other. So angle Y is going to be matching with J, so Y equals 72. And we're going to do the same, basically the same thing with these triangles down here. It's just going to be word problems. And this one has a picture for us already, but we're trying to find the width of a canyon. This is a canyon here. And this is a bush that's on the other side of the canyon. So we're going to see if we can use our measurements to see if we can figure out how wide the canyon is without actually having to go onto the other side of the canyon. So we have our small triangle here, which is kind of a flipped upside down version of this triangle here. So they are similar to each other. So that means this side right here, 10 and 7.5 come from the same triangle. We'll put those on top. 10, which is the flat leg, is going to match up with 100, the flat leg over here. And then 7.5 is the short leg, matches with X as this leg. So then we cross multiply. 10, I'll bring it up over here. 10x equals 750. And then we can divide by 10 on both sides, and we get x equals 75 feet. So this canyon is 75 feet across. Okay, go ahead and pause and read this very last one, and then see if you can come up with your pictures, your similar triangles, and then hopefully you can solve and answer the question it's asking. So we have a shorter ladder, which is 10 feet, reaches 8 feet up the wall. We have a longer ladder, which is 18 feet, and we don't know how far it reaches up the wall. So that is what we have to set up. So here we go. X and 18 come from the same triangle, so I'll put those on top. X matches with 8, 18 matches with 10. So we cross multiply. 10x equals 144, divide by 10, x equals 14.4. Okay, so we know this side is 14.4. However, this is like a typical ACT question. That is not the answer to our question. Because the question is, it says how much further up the wall. So not how far up the wall does the 18-foot ladder reach, or it's how much further. So this reaches 14 feet up the wall, 14.4. This only reaches 8 feet. So if we take 14.4 minus 8, that will give us our answer. So it reaches 6.4 feet farther up the wall than the other.